Hello, Justin.
Hello.
Oh, thanks.
I'm pretty good. Pretty good.
Yeah.
How about you?
Yeah, doing okay. I was a little worked out with the website falling apart, but I think after it got fixed, I feel a little relaxed. Yeah. I hope it didn't affect you too much. Like it was, I think, down for about 2 days, I think. Yeah. So, yeah.
I'd already downloaded the most recent homework, and since the video from last class didn't record, so I didn't have anything to look up, so I didn't need it.
Yeah. Good. Let's wait for Angela. Okay, I think Angela is here. Hello, Angela?
Hello.
Yes.
Hello? Yeah, I'm here. Okay.
Hey. Okay. Okay, let's see. How does it work? Oh, it doesn't even say it here. So there's a homework 7 that's due on Thursday. I think it is homework 7, right? Or is it? I think we did very few homeworks this week. Homework 8. Okay. Okay, 8. That's due April 30. Which is a Thursday. And that's the only thing remaining. But everything, if you have not submitted any piece in the course, make sure that you submit it by final exam, right? So final exam doesn't exist. It just acts like a deadline for everything, right? So when is the final exam, by the way? Wednesday. Okay. Okay. Anything you guys want to mention, point out? I did get a few, I think I got a homework from Justin, I think. I haven't graded it, and I got homework and midterm from Angela, but I'm not sure. Angela, it's very confusing because she's in both classes. I'm sure which class she. So I did get something from you, Angela, but I haven't replied to you yet. I was thinking I'll grade it, but I haven't got to it. Yeah. Okay. So what we have been talking about is radiation, but what we want to talk about today is, so let me change the camera. Yeah. So we have been broadly talking about radiation. And what we have talked about as of now, so radiation is there is some R prime sources down here, and you make an observation somewhere very far away, right? R, and typically we talk in terms of a dome around that R prime, and that is where the observations are made. We have talked about how much energy is radiated in a solid angle. So that's called how much is the change in the power, or how much power is radiated in a solid angle. So that's called angular distribution. So this is the angular distribution of the radiation. So whatever radiation is coming out, how much energy is going in there, how much going is in there with respect to some axis, what is the angular distribution of radiation. But most of the detectors that we keep to measure this radiation, they have this feature that they are color sensitive. Like you can differentiate between it is red light coming towards you or whether it is green light coming towards you. And the only quantity this says is what is the power that is radiated. It doesn't tell you, it gives you the time dependent contribution. The way we analyze this was, we can analyze this as a time dependent quantity. At some time it is here, sometime there is so much of power. But now we might be interested in, since our detectors are frequency dependent, instead of time dependence, it might be nicer to have frequency dependence. So we would like to know the frequency dependence of this power. Right. Frequency dependence. This is usually termed the spectral distribution. The frequency distribution is often called spectral distribution. That's it. So that's what we want to analyze. Instead of talking about power per unit solid angle as a function of time, we would like to talk in terms of power per unit solid as a function of frequency, because our devices are sensitive to frequency. And remember, frequency is a Fourier transform of time. So if you, a simple way of doing it is that take the result here and Fourier transform that quantity, and that should give us the right expression. But it is a little conceptually difficult because it's in the retarded time, and how a retarded time actually works out in the Fourier space, it gets a lot more complicated there conceptually. So we'll go back all the way to the first step, and let's redo everything instead of in the frequency space instead of the time space. So that's what our goal is today, and we'll use this result, whatever we get today, in the next class, to do what we'll call Cherenkov radiation, when things go faster than speed of light in a medium. So we are interested in the spectral distribution of quantities. So we go back to our Maxwell's equation. In fact, we'll go one step further. We said that in terms of potentials, we can have electric field and magnetic field. In terms of potentials is phi minus dA by dt. Everything is time dependent at this point. So we are talking in terms of position and time dependence. Magnetic field stays the same whether you're doing statics or dynamics. So that's del cross A, and the potentials satisfy the wave equation. Del square plus 1 over c square d by dt square of phi of r comma t is equal to 1 over epsilon naught times the charge and currents, right? And the same thing for A. So this is all the way we go back, and we want to retrace our path in the frequency space instead of the time space. That's what we're going to do. So right at this stage itself, we will change everything. Right, that's mu naught times J comma R comma T. Right. Once we have this equation, we immediately said that our phi is equal to phi is given in terms of the inverse of this operator. So a characteristic of this wave equation is what we said is a Green's function. So let me write that down maybe, or yeah, let me write that write the solution itself down instead of explicitly writing the Green's function. So this is R of t. This might need some space, so let me save it right from here itself. Phi of r comma t is 1 over 4 pi epsilon naught. Should I write it 4 pi there or later? So yeah, 1 over 4 pi epsilon naught. Then I do d cube r prime, that is dt r prime. This is sort of the superposition principle in terms of the Green's function. And the Green's function is where the retardation showed up. That's t minus t prime minus 1 over c times r minus r prime, right? So if you go back a few lectures, this is what we derived, right? And this is rho of r prime comma t prime, right? This was our expression. And the same idea for A, except that instead of 1 over epsilon, you will write mu naught, and instead of rho, you will write the current, right? Okay, so should I write the, yeah, let me write the A expression also just for completeness. Only once, and then rest everywhere it's understood that if I can work with phi, the ideas for the current pretty much go through the same way. Divided by r minus r prime, and that is j. Okay, all good. This was the summary. So this is our starting point if you want. And now remember that we are actually not wanting to work in the time coordinate. We want to actually go back to what we know is the Fourier transform of time, that is the frequency. So we immediately say that phi of the frequency dependence in the phi. So we want to go into the Fourier space. That's a Fourier transform of this. So you would do, you want to integrate over time. So you're integrating in time, dt. And the Fourier transform is given by e raised to I omega t of r comma t. So the point is that you want the whole a whole time dependence here, right? You go from minus infinity to plus infinity. All the time contributions contribute to the frequency. That's how it works. So our goal will be to start with this phi here, this expression, put it in here and write everything in terms of frequency. All this earlier we had an expression for radiation, the electric and magnetic field in terms of time dependent quantities. We want to rewrite it everything in the frequency dependent quantities in the radiation zone. Remember, radiation approximation led to a lot of simplification. Now, since there is a time dependence in here, it seems like maybe we can evaluate the time dependence in here and simply substitute this in there. So let's see how you go about doing that. So since I'm going to evaluate this, so think of these two together. I have to replace this phi in here. So I have three integrals now. I have a dt integral, I have a dt prime integral, and I have an r integral. I cannot do the t prime integral because that is t prime inside this charge density, and I want to keep the charge density very general, so I don't know what that expression is. But I can do the t integral here using the delta function. That will replace it only here. It won't disturb my charge density. So evaluate the delta function in using this quantity and do the t integral, and that gives me, so this t prime will stay. So that is 1 over 4 pi epsilon naught. D cube r prime stays. And t prime, there is no r minus r prime, so I push it across. So this is, so it is t prime, correct? So this is 1 over r minus r prime. So that's this quantity. The delta function leads to replacing this t with t prime. So, so when I replace t with t prime, there is an exponential that comes up, which has an r minus r prime. So this is I, t is getting replaced. So this is I omega over c times r minus r prime. Right. That's a replacement here, but that also gets a contribution from t prime, which I'm going to put it inside of the t prime integral. So this is an e raised to I omega over c times t prime times rho of r comma t prime, r prime comma t prime. Okay, so notice what I've done. I simply took this delta function, and wherever t comes, I have to substitute the argument of this being equal to 0. That's a contribution from delta function. So wherever t comes, I have to replace it with t prime and this quantity.
In the second
T prime
integral, why would there be a 1 by c in there? It's
why
just,
would there be a c? No, there won't be, because that's dimensionally wrong, right? Thank you, thank you. So that's omega. So that will be dimensionally wrong otherwise. Thank you. Yeah, so that's omega t prime, right? So it's omega t prime. That's one piece coming out of this, and the second piece that does not depend on t prime, I can bring it out. Okay, that's great, because this now is a Fourier transform of charge. I'm trying to get rid of all the time dependence and write it in terms of frequency. This is nothing but the Fourier transform of the charge distribution. So this is equal to, if I can put this all in here, 4 pi epsilon naught, or yeah, hopefully I can squeeze this in. Is this readable? Readable? Yeah, okay. So this is e raised to I omega over c times r minus r prime over rho of r prime times frequency. So instead of time dependence, I suddenly have the charge in terms of frequency dependence, because that's a definition, right? Fourier transform of the charge density is basically r omega, and that is the contribution. So basically we have electric potential in the frequency space given in terms of the charge density in the frequency space, and the Green's function now is now no more 1 over r minus r prime. There is an exponential feature to that, very much a signature of something like a Yukawa potential. If we realize that this is if this I was not there, it is very much a Yukawa potential, and Yukawa potential has to deal with an exponential tail instead of a 1 over r potential. There is an exponentially decaying piece to that potential. But anyway, so that's our electric potential. So the same thing works for magnetic potential or the vector potential also. So let's write that down. So if I were to rewrite this, so we have phi of r comma omega. I have 1 over 4 pi epsilon naught. Just simply rewriting e cube r
I have
prime.
a rather elementary question. In the previous step,
But
the second integral, you wrote it down as rho of r prime omega, right?
Yes.
Because that's a Fourier transformed.
Yes.
So usually there is a rho tilde. It's a different function, isn't it? Or does
Yeah, it is a different function. Actually, I should always say that. So here, even here, right? This is a different function, okay? But then Fourier transform is always done in that, and eventually you get out of letters. So it's understood that this is a different function, and the dependence is what is telling you that this is a different function. So technically what you're trying to say is that this should be phi tilde.
Yeah.
Right? That should be phi tilde, this should be rho tilde. If that helps you, that's good enough, but that's I'm trying to say that if there is a frequency dependence, that's a separate function. That's of course it has to be that it's not possible otherwise this integral. I think only the Gaussian has this feature that its Fourier transform is also a Gaussian function, but even then it comes up with some constants and all in front. So it is not, it's not identical. So the dependence is not the same. So we rarely have such dependence. So yeah, how about this? So now that we have just begun, let me try to keep the tildes. I think it doesn't matter. I think here it's okay, but I think when you're typing things up, there's too much clutter there with the notations there. But in the beginning, maybe it is good. So let me try to keep the tildes.
I just wanted to clear. I mean, you can still keep on using the same function. I just want to make it clear. That's all. Now we can.
Yeah, no, good point. Let me see if I can keep it in this class alone. I may not keep it in general all the way place. Yeah, good. Thanks. Okay, that helps to clarify. So this is exponential of
The board.
I.
The board.
Oh, about I don't move it around here. Okay. Yes, thank you. So this is I omega over C, and then this is R minus R prime, and divided by R minus R prime, right? And this is rho tilde now. So this is R prime. Notice if you were doing statics, correct, you don't worry about frequency. And so how do you get statics out of this? In the Fourier space, how do you kill the time dependence? You put basically in the Fourier space, it is equivalent to putting frequency equal to 0. So if you were to put frequency equal to 0, that becomes statics. So that's a good thing to realize, that time dependence, if it was not there, so that is a basically static situation. How do you see that in the Fourier space, it is omega equal to 0. So 0 frequency involves statics. How to see that is 0 frequency means 1 over time, right? Frequency is 1 over time period. So if frequency is 0, time period is infinite. So if time period is infinite, that means it is never coming back. So any periodicity is killed. So within one period, it is seeing the whole nature, or it is hardly changing in that period. So that's one way of looking at it. And the same thing with vector potential. Now, frequency dependence, I didn't do this, but I think the same idea goes through. And this is d cube r prime. So this is the modification of your potential, 1 over r potential in dynamics in the Fourier space, the frequency dependence of your electric potential. Right, that's your j of r prime, or j tilde now. Right, so it's a vector and a tilde there. So that's omega. Okay. Okay, that's good. We are working, so this is all very generic. No, this is not about radiation. This is always true, right? If you're working in the frequency space, this is always true. Let's immediately invoke radiation. So radiation involved. The idea that r minus r prime can be approximated to r minus r prime can be approximated to, you take the square root of r square minus r to r prime, right? So maybe I should write that is equal to square root of r minus r prime. R square plus r prime square minus 2 r dotted with r prime. That's exact. But in the radiation approximation, this is the same as approximately r. You bring it out. This is second order. I don't keep that. And in the leading order, when I take square root 1 by 2 and 1 by 2, that cancels out. Divide it out, so you have r hat dotted with r prime. Right. That's approximation of radiation. And when you do this approximation, in the denominator, I don't have to keep the next order. To capture the leading order, when it comes to the denominator, I have to keep only the r. But in the exponential, I have to keep both. Okay, so that's how it works in radiation. And we saw that earlier in detail. So basically, this exponential I omega over c r minus r prime over r minus r prime in the radiation zone is I, so this is e raised to I omega over c times r over r, right? That has both in it. But there is one more piece that's coming from this quantity here. That's r prime dependence. So this is having a minus I omega over c times r hat dotted with r prime. Okay. So that's the like this is the simplification in radiation. This is our Green's function, if you want, or the electric potential due to a point charge having a particular frequency, or the time dependence contained in a frequency. And this is the approximation that leads to the radiation. Like most of it is having this 1 over r potential. Forget about the origin, but there is a phase still involved, right? That's the point. At this point, let's introduce a nice feature here. That is omega over c times r hat. So omega over c is like frequency divided by velocity that has a 1 over wavelength in it. So let me say this is 2 pi over lambda. So this is my definition now. So there is a lambda I invoke. And let me also say that's the magnitude k, right? Wave number, right? So this is just a notation at this point. But I want to associate a vector with this. So I would say that omega over c times r hat. So notice k is a scalar quantity, but associated with an r hat, and that's going to be k. That's my k. So the magnitude of k is simply omega over c. Like, so it's a very restricted k here. It is not having all the freedom with that choice. So this is a notation now. So and not only k, I want to say k prime. Okay, so this is going to be k prime. And in that, I can say that this is k prime now here. This is whole thing is k prime. Why do I do that? Because then it has this Fourier transform feature in there, right? Position, if I'm Fourier transform, there is a position wave vector that comes up. And we will see that there is something to do with k prime there. But as of now, it is just a definition. Frequency, what is frequency? It is the frequency dependence of the sources and currents. And in the frequency times the direction in which we are observing the radiation, that is at k prime. Well, this will come back as we proceed. Okay. With that, if I were to write down my scalar potential now again in the frequency space, So this is r comma frequency, that's equal to 1 over 4 pi epsilon naught, and many things can come out because there is no r prime dependence in there. So this whole thing can come out of my of the integral. So that's 1 over 4 pi epsilon naught e raised to if you want, I can simply say this is e raised to I k r, right? So, but let me just say this is so this is e raised to I omega over c times r divided by r, and then inside of the integral I have d cube r prime e raised to minus I k prime dotted with r prime and rho of r prime comma omega. That's very nice because now I can interpret this as a Fourier transform of this rho in the position space. This is not the Fourier transform in the time space. This is the Fourier transform in the position space itself. Right? Position space also can be Fourier transform, and then it becomes algebraic. Then there is no integral to work on. It becomes completely algebraic, and let me write that down. So there's a lot of simplicity in when you go in the frequency domain. This is 1 over 4 pi epsilon naught. And let me also say, so there's going to be a difference. So if we set k is omega over c, k prime is having an r hat in it, right? So keeping that in mind. So if you want, I can write once, I will write this explicitly, and write once I will write it in terms of r. So this is r, and this is rho of r prime is actually omega over c times r hat, right, times omega, right, which is nicely when you think of it as in terms of the variables. So it is e raised to I k r over r, then where k is understood to be omega over c, and rho here is actually k prime. No, I think I didn't mean to write this as a k prime. Sorry. Yeah, I don't mean to write k prime. There's no need to write k prime, right? This is k, and the magnitude of that is, yeah, I don't need prime there, right? So that's just k. Okay, so that's k and omega. And I forgot to write the tilde where I started dropping the tilde. So this is tilde. This is tilde. In fact, at this point, this should be double tilde, right? If you notice, this is first we started with position and time, then we went from position and frequency, and now this is a wave vector and frequency. So this is a third vector. So in principle, this is double tilde. I think probably that's why I drop writing this tildes, and it's understood that all these are different functions. Okay, that's reasonably nice. Simple expression, no integration, so it is algebraic. And the same thing for vector potential. Right? So vector potential is r comma omega is equal to mu naught over 4 pi and e raised to I k r. Again, k seems like, oh, there is a k on the right hand side, but not on the left hand side. But remember, k hat. So the vector k is omega over c times r hat, right? That's that information in there. So don't forget that k is not really wave vector, but it is a frequency dependent quantity. So this is j. Again, double tilde if you want. I think I should stop writing tildes there. Yeah, I think it's too much clutter otherwise. Yeah. Okay, so that's your scalar potential and vector potential. Now let's we are interested in the electric and magnetic field, correct? So let's do more work on this. Right. So we need to actually get a gradient of the magnetic field is so magnetic field as a function of r and t is actually del crossed with the a, right? Oh, sorry. It's clear that if I were to take a Fourier transform, this will simply get replaced with omega. So that's clear. I just have to integrate since this is a position dependent quantity that doesn't change. So this will be omega. It will be equal to del crossed with a of omega. Right. So what will this be? I substitute the value of a in here, right? So this is equal to the curl of whatever we found. So this is mu naught over 4 pi, and that is e raised to I k r over r, and that is j of k comma omega. Okay. Now notice what is happening here. This has to start hitting all the r dependence, correct? This gradient has to hit all the r dependence in there. There is an r dependence in here. So let me put an arrow there. So this is an r dependence in there. There's an r dependence in here. And there is also an r dependence in there. Right? Remember, k is omega over c times r hat. Right? There's an r hat in there, right? But remember, we analyzed this in the time dependent case. We are in the radiation zone. We want only the leading order contribution, and the leading order contribution comes only when it hits this this r. Like when it hits your r here, that is a 1 over r square contribution. When you hit this k, that also is a further down, because the gradient can be converted into a time and a gradient, so that also is a higher order. So it is only when it hits this r there that leads to actually a or the leading contribution comes in. So this is going
What
to be,
happens when the gradient hits the r in the k? I thought it was not, it was omega by c.
no, there is a
r.
r hat. Yes, there is a r hat in there. So remember, gradient of r hat, right? So this will give you a gradient of r hat eventually. Like, of course, it will hit a gradient of the j itself. So if you want, I think what you're talking about is gradient or curl, basically curl of j is basically you're saying make a chain rule, right? So this is eventually gradient of r hat and gradient with respect to k crossed with j, if that helps. So this is j, and this is a dyadic now where this has to be going with dotted with here. So let me put it, how should I write this? Let me write that on the other side. Yeah. So this is dotted with gradient of r hat, which is r over r. Does that help roughly?
Mm-hmm. Okay.
Right. This is the chain rule. First, I take the derivative with k, and this is the derivative of k with respect to r, right? But now notice here there is a 1 over r, and that will become 1 over r square, right? So that we don't want, we are not interested in, right? All the 1 over r square relative to 1 over r is negligible. Does that help?
Yeah.
Okay, so that's the argument that, and the same thing came in time dependence also. So one has to be, and there are two terms, of course, there is a, this can hit this one also, but then again, there is a 1 over r, and there is this gradient in here also. So overall, it is not contributing. Okay. So keeping this alone and arguing that that is of higher order, which comes out more explicitly actually in the time dependence case. Here maybe it is a little, this part might be a little not completely obvious, but in the time part that comes out clear. Okay. With that argument, we say that, oh, so that is going to be hitting here. Remember that gradient of r is simply r hat. So it is, when I take the derivative, it is ik times r hat. But ik times r hat is simply vector k. Right? So it seems like, so this is I times k times r hat, because that's what comes out of here. So this I times k is the derivative coefficient of that. And this is because gradient of r is this. It's crossed with mu naught over 4 pi times e raised to ikr over r times j of k omega. Okay. Or better, this is simply mu naught over 4 pi, or I can also write this as, so basically what has happened is that I have replaced my gradient with I of k. That's all that has happened. Right? So this is basically equivalent to saying that I have replaced the gradient with k. Right? That's nice. So basically the same thing can be done with the gradient of phi, because electric field similarly is negative gradient of
What
phi.
happened?
Yeah.
Is it supposed to be A, IK cross A or J? Because
Oh,
what happened?
yeah. Sorry. I start thinking about the next line while I'm writing that. So yeah, very correct here. So it is simply gradient gets replaced with I times k. There is a similar things that's happening in the electric field, d by dt of A. Okay. And same thing happens here. So this is equal to minus I times k vector times phi of r comma omega. That's
I
going
have
through
a
the same
question.
argument
This is
again.
probably going
Yeah.
back. So why did we not even consider the 1 by r square? Are we saying it's only in the near field of the source
Yes,
or something like that?
1 over r is more dominant than 1 over r square.
Okay. I mean, yeah, but r square is not that. I mean, it comes up in the equations though, right? R 1 over r square. So is there any, are we considering only the nearby points from the source?
No. We are saying that we are very far away actually from the source.
Okay.
When you're very far away, r is very large. So when you're very in the very far region, 1 over r is way more dominant than 1 over r square. We're talking, let's think of it as the source. So this is, so the actual quantity is r over r prime, right? R over r prime. So think of r prime is inside an atom. Like typically we are talking about an atomic regime. So that even if it was a micrometer, so this is approximately 10 raised to minus 6 meters. And in your lab, the position might be 1 meter, or let us even say if it is small enough that it's 1 centimeter, right? That is also perfectly fine. You might be having a sample and having a detector only 1 centimeter away. That's about how much? 1 centimeter is 10 raised to minus 2 meters, right? So that's about 10 raised to 4, right? A dimensionless quantity which is 10 raised to 4. That's huge. Correct. And we are getting a square of this quantity. So in principle, even though we are not writing it, if you were to explicitly see this, this will all be in as a dimensionless quantity. It will come out as r prime over r. In the next term, whatever we are talking about, it will be r prime over r. And that means square will be 10 raised to 8 with respect to 10 raised to 4. That's really small. So it is negligible. So even it doesn't show up in 1% accuracy, it doesn't show up. But I should say that these things are all fine. But one has to be a little more careful when you're doing high energy physics. Like high energy means if you're working with things moving very fast, then we have to be a little more careful.
I'm sorry. So is it 10 raised to 4 or minus 4?
10 raised to 4, right?
So it's a square of it, or it will be more, like a bigger number, right? I thought the argument was that the square is supposed to be
Because
small.
it is a reverse that is coming, right?
Okay.
So everything is in 1 over r. So the series is, so there is a 1 over r. So this is how radiation works, okay? So there's a 1 over r in the outside because of dimensional reasons, okay? And the first term will be 1 plus the next term will be r prime over r, okay? Order of this. There will be some coefficient in front. That will be an r prime over r. And the next one will be r prime over r square. There will be some constant here. So let's say A is A1, this will be A2. Okay. So this will come out to be 10 raised to minus 4.
Yeah.
And so this is the 1 over r square that we're talking about. It's not 1 over r square, it is 1 over r times r prime over r. In that sense, it is small. And this is very being conservative here. It's actually much more small. But this can get, our scenario can change if things are moving significantly faster. So there is also this approximation that how fast are these particles moving. So when I say the source is moving, if we are talking about molecules, like air molecules, like that's kind of a radiation we talk about, or even a small molecule inside a sample, then that's perfectly fine. So they move very slowly. Even if they're moving, they might be going at 10 raised to 3 meters per second. That's significantly smaller than speed of light. But if you're talking about electrons moving inside an atom, or let's say just a high energy particle in CERN accelerator, they are extremely moving, they're going very fast. In that case, this might lead to a small correction. It's not here. This is, where is that? Where is the C showing up? So that is, where did that? I think in the retardation part, it comes out better. So the retardation part is TR is equal to T minus R over C plus R hat dotted with R prime over C, right? Right. This term sometimes can contribute. Most of the times it doesn't contribute. This term sometimes does contribute. This is the same term that is showing up here. This is, where is this? The Fourier transform that is showing up in the row. So this K prime, that R hat that we have inside here, that's coming from that. So that can sometimes, the phase can show up in relativistic scenarios. So one has to be careful, but most of the time, at least these discussions are surely valid for non-relativistic molecules. High energy, one has to be a little careful. And that's mostly known as synchrotron radiation, which again is not very difficult. Do this a little more carefully and take up all the phases coming from there, and that works out fine. Does that help in that? Okay. So it is, maybe the way to say it is that Yeah, what is the complication with radiation? Yes, radiation involves an approximation, and the idea is to get all the leading order contributions correctly. So make sure that we don't miss anything. And that is true with any approximation all the time, that one has to be careful that we are actually not dropping away something that is relevant. And this is true for non-relativistic scenario for sure, okay, if that's bothering. Okay, this is also a time dependence showing up. Time dependence, how does that go into frequency? So this is kind of a wrong thing to write here itself, because what is this acting on? There is no time dependence in here, right? So at this stage itself, I should have written a straightforward time derivative becomes minus I omega. So it is plus I omega times A of R omega. Like this is not an approximation. This is always true for any function, but the gradient becoming an I times K is not very obvious. That is only in the radiation approximation or in the non-relativistic radiation approximation that that is actually happening to be true. Okay, so that's good enough. But now we want to do something more here. Like remember that we had this feature in time dependence that we could write everything in terms of current. It was not necessary to write both the charge and the current. So can we write everything in terms of the current? So let's proceed a little further in equation and write this as so let me bring out that this has the rho and current in it. So let me put that all together. So I have 1 over 4 pi epsilon naught. So this is minus of 1 over 4 pi epsilon naught times e raised to ikr. So maybe right. So e raised to ikr over 4 pi r. So that's all common. So maybe put that also in here. So this is minus and a minus here. So this is minus ik times phi depends on rho. So this is rho of k omega and plus I omega. Oh, sorry, there's an epsilon naught also. So there is ik over epsilon naught. And there is an I omega. And then there is j of k omega over times mu naught actually. Times mu naught. With me? Right. So what I did was replaced phi with the expression we had for in terms of rho and replaced A in terms of J. And can I write one more line there? Yes. So this is, I'll do one more thing so that we can actually what should I do? Yeah, let's keep it as it is. Right, is this correct? Is this right? Is this right? Yeah, let's keep it as it is. And like we did in the time dependent case, to convert this completely into the current form, we have to invoke the current conservation. So remember, oh sorry, charge conservation, right? I keep telling. We have gradient of dot with J. Sorry, divergence of the current plus time derivative of the charge density is equal to 0, correct? And the same thing here, there is a R function of time. Fourier transform this in both the space and the time, and we will get time gets replaced with minus I omega rho of, I'm going over to the space Fourier transform 2, so that's omega, and the same thing with plus ik hat dotted with j. Correct? That means to say that I can replace my rho with k dotted with j replaced by omega. But if I am writing actually k hat to be k, I can replace k omega. Then there is a simplification here that rho of k comma omega is actually I cancels out. Omega is pretty much c times k, so there is 1 over c there. So there is 1 over c, and that is r hat. Or maybe I should write it in terms of k hat itself, or r hat. Let's see. Yeah, let me write it as r hat. So this is r hat dotted with j of k. Remember, k hat, k vector is omega over c times r hat. With that, I can actually put everything in the top expression, and I'll get a simpler expression for E. So this will have a k vector, and there is an r hat, but there is also an r hat in there. And we will see that this is actually a cross product that is coming up. So let me try to replace that here itself. So this is omega over c times r hat. So this is omega over c times r hat. So so let me write electric field as, if I can, let's see if I can put this together here. Let me pull out a mu naught and I omega also out. So I omega mu naught is being pulled out. So I times omega times mu naught over 4 pi e raised to ikr over r. I omega is gone, so there is a mu naught I have pulled out. So this becomes a c, right? So that's c times rho, which is nothing but r hat dotted with j. So this is minus of r hat dotted with j, where j is a function of k and omega. And I've already pulled out rest of them, so that's plus j. If I were to pull out the negative sign also, so this becomes plus, and that's a minus. Which is nothing but r hat crossed with r hat crossed with j. So this is nothing but this bracket quantity that is showing up is r hat crossed with r hat crossed with j. Okay, so that's the idea. So let me put this all together. Let me summarize what we got as of now. So maybe put it here. So what I have here is electric field. Sorry, magnetic field is better, right? So if I were to write the magnetic field, let's say C times B, I should write. So magnetic field is C times omega over C, right? Yeah, so magnetic field times C, so C times B of R comma omega is equal to I times omega. So I'll write this as minus of R hat crossed with, right? So this is the same expression we used to have for, in the time dependent case, there used to be a K we used to call the integral of the time derivative of the currents. And here in this case, this comes out to be mu naught over 4 pi times e raised to IKR over R times J. But now the time derivative of J is encoded in this frequency dependence minus I omega. Okay, that's a way of writing this so that I can identify this with time derivative in the time zone. And this is J of K omega. Okay, again, notice in the time dependent, this would have been an integral because this is a Fourier transform, and this would have been a time derivative, like and with the retardation into picture. Electric field in the same spirit, we have seen is a cross of this. So you would say this is minus R hat crossed with C times magnetic field. Same features, except this piece has changed now, right? We would have written it in terms of integrals, integral and position there, and with the retardation showing up. And again, we have C times B can also be written as R hat crossed with E. Okay, so that's a nice feature in there. Okay. Any questions at this stage? So these are all the fields, but we are usually interested in the power, right? Power radiated in the far field region, and the power involves usually R cross K, and we would like to integrate over that. And let's see, I think how much is this? Yeah, let's quickly, let me do this, at least build it maybe. Or should we postpone it? Yeah, let me do this, okay? Yeah, I have 10 more minutes, right? So that, because we have only one class left afterwards. Okay, we are interested in the power radiated, and we already showed that the power radiated, which is the energy, so dP by d omega, correct? Which is basically the change in so second derivative change in energy with respect to time and per unit solid angle, or you can say energy per unit time per unit solid angle, right? That's what it is, and that's equal to I think yeah, I can directly use this. I suppose I don't want to derive this again. So this is equal to negative. Why is there a negative? Help. Yeah, it's negative in the sense that if we think of a volume of space, energy is being lost outside. So if you talk about how much energy is going into the solid angle, that's a positive quantity. But if you were to derive this inside a sphere, that comes out to be negative. But we want the positive quantity with that interpretation in there. And this comes out to be 1 over mu naught times C R square times C times magnetic field. This is time dependent now. Right. We did this in a week ago. Right. We started with E cross B. So notice S, the Poynting vector is E crossed with H, right? So that is E crossed with B over mu naught. Right. And then we want to take R dotted in the radial direction. So we'll take a cross or a dot product of this. So cross and dot changed gives you a, so this is R dotted with S, or hat dotted with S, gives you a magnetic field square. Right, that's the idea in here. And since we are integrating over at a very far spherical regime, so that's the R square then, since we are integrating over a sphere. Right. So that's good, but now we want to get the Fourier transform of this. So that's a key feature in there. Okay, so let's do this. So let's do the Fourier transform of this. So basically take the time derivative and get a Fourier transform of that whole quantity in there. Okay, so any questions? So I might shoot by 5 minutes more, but then if we finish this off, then next week or next class we have a little more freedom to with the time. Okay, so the power, energy radiated per unit solid angle. Right, so let's talk about the energy per unit solid angle. That means total energy. That means I am integrating over all time. So what is this equal? So this is energy, not the electric field. Okay, that's, so what I'm doing is I want to do minus infinity to plus infinity dt times d by dt over dt times d omega. Okay.
The board is not visible.
Oh, the board is not visible. Yeah. Okay. Sorry about that. Okay. So yeah. So yeah. So how do we proceed? Correct. So this is equal to, we already what we're going to do is yeah. So what we are interested in talking about the 2e over the frequency times omega. So notice this is energy per unit time per unit solid angle. I would like to know what is the energy per unit frequency per unit solid angle instead of time. Like that's what I'm interested in. So how do I go from here to there? Because I know everything in terms of frequency now. can I do this? So for that, what I will do is I'll get rid of the time here by integrating out, substitute the time dependence in, and bring out the frequency somehow. So let's go about in steps here. So this is minus infinity to plus infinity dt. I know the expression for this just now. So that was equal to mu naught over c, right? So this was, so that was an r square and mu naught times c, right? Substitute that. And this is, and there is a c square also, I think I can put it in. Yeah, let me, so this is c times magnetic field r of t dotted with c times magnetic field r of t. Right, perfectly okay. This was squared actually, right? So instead I split that into two. And now I'm going to put this into frequency, everything, Fourier transform the whole thing. So this is mu naught times c minus infinity to plus infinity dt, and Fourier transform this in the time. So time will be d omega over 2 pi minus infinity to plus infinity e raised to, oh, I can also do one more thing. These are all real quantities, right? Let me do, since it is squared, I can also say, since it is real, I can also say this is star. Right? I don't lose anything. But in the frequency space, that star does do something, right? So that's just a, using that fact. So the Fourier transform now becomes plus. Usually it is minus, so that becomes plus because of this star. So that's plus omega times t and b c times b of r omega now, right? And that's a star now. I take the Fourier transform and star it, and Fourier transform need not be real. Right? Fourier transform of a quantity need not be real. Dotted with the same quantity in another frequency. So this is minus infinity to plus infinity. Now it is d omega prime over 2 pi. This is e raised to minus I omega prime. T remains the same, and c times b of r comma r comma omega prime, I suppose. Okay, clear? Move the time integral in. Time comes only inside the exponentials. That's r square mu naught c d omega over 2 pi. And again, I should mention that this is a standard trick you use all through and Fourier transform. This comes again and again. So this is minus infinity to plus infinity d omega prime over 2 pi. And this is c b r omega star dotted with c times b r omega prime. So this is not a dot product yet, but now the time integral can be pushed all the way to the right, and that's doable. Omega minus omega prime times t. And that's a delta function, right? This is a delta function. In fact, 2 pi times delta function in frequency. That means to say that this omega and omega prime has to be at the same frequency, right? Once you have a delta function, that can be used to get rid of one of the integrals there. So that gets rid of one of the integrals too. And what we have is r square. Let me now write the whatever we started with. So this is energy that's thrown out into one solid angle. is equal to R square over mu naught times C, and that's minus infinity to plus infinity d omega over 2 pi times C times B of R comma omega magnitude square. Let's whatever happens in one side of the frequency will turn out to be the same on the other side of the frequency also. So let's put a factor of 2 in here. So let's change this to 0 and actually multiply this by 2, with the fact that usually we say the frequency that we are interested in is from 0 to omega. And in that case, bring out the frequency dependence to the left. So now we can say the energy radiated per unit frequency now, per unit solid angle is, there is a pi that remains after I multiply by 2. So there's a 1 over pi. Here omega now is less than infinity and greater than or equal to 0. Okay. You can write it in terms of negative and positive frequency also. That's just a way of doing this. And then there is R square over mu naught C times magnetic field now in the frequency regime, right, which we have calculated. Like, and the magnetic field had this 1 over R dependence everywhere. So that 1 over R dependence cancels out exactly. So R square is gone. So that was the idea of keeping the R 1 over R dependence. So if you take the higher order dependences, you have to be careful. Only the phase dependence are crucial in there. And that leads to the energy per unit solid per unit frequency. Next time we will come and evaluate this for a very particular scenario. Usually it is nice to think about radio antenna itself that we talked about. Actually, your homework begins from here, right? So this expression and the magnetic field itself is given in terms of current in the frequency regime. So we think of an antenna that we talked about last time, but we take a circular antenna and we say that there is charge going around, and we can calculate the frequency dependence in there. And we are interested in evaluating this piece. It involves Bessel functions, but we have seen Bessel function in some form or the other earlier. So, but it doesn't invoke too many properties of the Bessel functions. Everything is given in the problem. So just follow the steps in the problem. I think it's just broken into small pieces. Again, feel free to ask me. There are lots of mistakes I've been making this semester, so I'll let me know, okay, how it goes. And on Thursday, we'll start from here and finish the CERN co-radiation. Okay. Thanks.
Thank you, Sujesh. See you Thursday.
See you Thursday. Yeah. Thanks, Justin. Yeah. Bye, Angela.